Alright, welcome to another AQA A-level chemistry video. Today I'm going to be making a video on buffer solutions. And in previous videos I talked about buffer solutions in terms of, I mentioned it when I was talking about pH curves, like the start of the curve, it doesn't change pH very much. And I said the axis kind of has similar traits to what a buffer solution is. So in this video I'm going to be talking about what a buffer solution is, uh, why they're used, how they work, and how to go about understanding the basics of calculations towards buffer solutions. And in my next video, I'll be doing actual exam questions related to buffer solutions. Now, I'll just get straight into the video. So, buffer solutions oppose small changes in pH, right? So, what is a buffer solution? So, a buffer solution is just a solution that opposes pH changes. And really, what I should say here is that a buffer solution is any solution that maintains the pH, well, maintains a specific pH by opposing changes in pH. And this means that if you add acid, the buffer solution removes it to keep a constant pH. Now, and it's the same thing for bases, right? So if you add acid, the buffer solution removes any acid to keep it at that specific constant pH, to remove any excess acid that may have been added. It will also remove any, if you add base, the buffer solution removes any base to keep it at that constant pH. Now, in reality, if you remember when we looked back at our at the pH curve, right, it doesn't keep a completely constant pH, but they do reduce the size of any changes, and it's very good at doing that. So if I go back to this previous video where I talked about, if I want to talk about the pH curves, right, like this here, right, so this part here said it kind of acts as a, I'm going to highlight this part here. I said this part here kind of acts like a buffer, because this is what happened. This is what happened here, right? It just means a buffer solution maintains a constant pH by opposing any changes in pH. And this is what happening. We're adding base in this case. This isn't meant to be a buffer solution, but it's kind of acting like a buffer because we're adding base in this case to a, well, in this case it's a weak acid, but it's maintaining the pH very well. Of course, it's still slightly increasing, but the increase is very, very minuscule. It's negligible, you could even say. I mean, it's not really anything significant in terms of the increase in pH, right? Until it reaches a certain point where the concentration of base is greater than or equal to the concentration of acid, and then that will increase. Then the property of the buffer is lost, and we have a significant increase in pH. And this could be, you could have an acid buffer, a basic buffer, or even a neutral buffer, right? There's certain, we even have in your blood, there's certain things in your blood that actually act as a buffer to maintain a constant pH of your blood, right? So there are buffers in your blood, blood as well, to make sure that you maintain a constant, roughly neutral pH. I believe your blood is slightly alkaline, but it's roughly seven, right? And you're trying to maintain a constant pH and you can obviously tell why, to maintain optimum conditions so that your enzymes don't denature. But the point being, right, that they just make sure that there's no significant increase in pH, so you're maintaining constant pH by opposing any changes in pH, right? That's all they do. So if there's a change to pH, it just if there's any acid added, it neutralizes it by reacting with a base to usually form water or some sort of salt, and that would decrease any did I say acid or base? Yeah, if you add more acid, let's say that we added, in this case we added more acid right to this, and it went slightly down. I don't like it. I don't want to use the highlighter. Say it went slightly down, it would react with a base to increase it would react with a base to get rid of any H plus ions that we've added on, and then that would remove any H plus, and therefore, and we to want to replenish. You see, it's more like an equilibrium. It will shift to produce more base, and that helps us to actually go back up again. Really, they won't show it on a graph like this, but really, realistically, right, any change to pH. So as I said here, if we're adding more acid, reactive base that removes the acid, equilibrium shift to the right to produce more base. We've returned back to our regular pH, or the pH that we want to keep maintain at that buffer. So if I just go back, this is just kind of to get you a brief understanding of what I meant there. Hopefully I didn't stutter too much, and you understand what I was saying right there. But how does the buffer solution work, right? So I kind of mentioned equilibria, using up products, is a products of base and acid to react with any additional acid or base that's reacted to remove any of these additional base or acid so that we can prevent any change to pH, right? So how does buffer actually work? So buffers work through changes in equilibria, and an acidic buffer will contain a weak acid and a salt of a weak acid. So these are the key things that you need to know. So a weak acid is, so an acidic buffer is a weak acid and a salt of a weak acid. And you need both of those to work together in a solution to actually to actually work as a buffer. And both equilibria are have use, and I'll show you what I mean later on. For example, methanoic acid and sodium methanoate, the important equilibrium is so if we're having methanoic acid, and here's an example of an acidic buffer, right? Methanoic acid, which is a weak acid, carboxylic acids are always weak acids, and sodium methanoate, which is a salt of that weak acid. So as you have sodium methanoate, you have lots of methanoate ions, because sodium salts completely dissociate in solution. That's one thing you need. Remember we said acids weakly dissociate in solution, but salts fully dissociate in solution. And according to Le Chatelier's principle, we will remove lots of H plus from solution to reduce the concentration of methanoate ions, and this means that you have lots of unionized methanoic acid. So I'll show you an example of what I mean here, right? So why both of them work together. So this is what the two equilibria would look like, right? So equilibria, okay, so we have CH, so methanoic acid, right? In theory, dissociate. Oh. So that's the first one. That's dissociation. It still technically does this. It is an acid, so it does dissociate H plus ions in solution, but not strongly because it's a weak acid. And now you have the second type of equilibria, which is the salt of the weak acid, which is sodium methanoate, which reality looks like you don't have to draw the minus and the plus just to show you that it is a salt. So it has those two properties there, and they just cancel each other out. Right. Now, why is it important that we have this? Because they have two different levels of equilibria. So in the first equation, it's fair to say that equilibria, because it's a weak acid, it doesn't fully dissociate. It does dissociate ions in solution, but it does it very weakly. And so we say that equilibrium is to the right, but very, very weakly to the right. Right, so if I just use this here, right, we say it's more in the middle, we said, right? So because of that, it means that we have in solution, we have a very high concentration of reactant, because very little of methanoic acid dissociates in solution, and we'd have, because of that, therefore we'd have a very low concentration of our products. So we have a low concentration of methanoate ions in solution from that equation, and a low concentration of H plus ions in solution from that equation. Now it's the opposite now for the salt. The salt fully dissociate in solution, so equilibrium is very far to the right, right? Ooh, sorry about that. Equilibrium is far to the right, and we have a, because of that, because the equilibrium is far to the right and it prefers to dissociate fully in solution, we have a low concentration of our product of our reactant, which is the sodium methanoate, but we have a high concentration of our methanoate ion from this equation, and a high concentration of Na plus from this from this reaction here, right, from the dissociation of the salt. Now, why is this useful, right? So adding an acid to an acid buffer. So if you add acid to this buffer solution, then the methanoate ions will react with the hydrogen ions and remove them, right? And this will reduce any changes in pH. So if we add, so let's say that we, so this is a buffer. It's an acidic buffer, so it maintains a pH of roughly, let's say roughly 5 or so, right? It's a pH of roughly 5, nothing too acidic, roughly 5, right? But let's say there was a change to the condition and it suddenly became more acidic. But there's a reason why it doesn't go completely too acidic, because if there's an increase in the concentration of H plus in solution, right? So let's say move that now. So it's no longer low, it's high. Right? So then any H plus that's been added will cause, it will react with the methanoate ions. Remember, we don't have a high concentration of methanoate ions. We don't have a high concentration. Remember, you have a low concentration of methanoate ions. But technically, in solution, this is all in the same solution, or all in the same beaker. We don't. We have a high concentration of methanoate ions here. Remember, from this equation here. So any H plus acid that's being formed, so any H plus acid that's in our solution that's been added will react with the methanoate ions. So all of this would be reacting, right? So first of all of this would react, and that causes equilibrium to shift to the left. Any increase, and then we still have some H plus left over, right? So we have any of this excess H plus that's in a solution will react with the methanoate ions that's also in solution. That's also caused from the dissociation of the salt, and that causes equilibrium here to shift to the left to produce more methanoic acid. But so it produces more methanoic acid, but when you do that, you've now decreased the concentration of H plus, and now in solution, because we've used the methanoate ions, we've used the methanoate ions here to react with any H plus. We've now reduced the concentration of H plus. Because remember, in our solution, we have quite a high concentration of methanoate ions, and also quite a high concentration of H plus. We've now used H plus to react with the methanoate ions. We've now reduced the concentration of H plus. We've reduced the concentration of methanoate ions, but not significantly now. It's now much lower because we've used up methanoate ions, but it's now back to the methanoate ions have just gone back to the solution the concentration that they already have. Because remember, these methanoate ions will dissociate in solution. So we haven't used up any methanoate ions that have been used up, right? We can easily reform them again. It wouldn't be difficult for us to reform them again, because we have two reactions that are undergoing in equilibrium here, right? Hopefully this makes sense to you. But we're just reducing the concentration with any increase in H plus, right? If we go back to the beginning, any increase in H plus will react to methanoate ions, right? Will react to methanoate ions to cause equilibrium to shift to the left, to reduce the concentration of H plus, and then to replenish the concentration of methanoate ions, we have this second reaction here that's occurring in equilibrium in fact, this reaction will go even further to the right to reform the concentration of methanoate ions in our solution, right? So that's if we increased, and then this will all return the pH back to the original pH that we had in our solution. So that's how an acid buffer maintains pH when we add acid, right? And then eventually this concentration of H plus will become low again, because we used up all the any increase in H plus with the methanoate ions, right? And eventually over time, the equilibrium will return for the first reaction to go back into the right or back into the middle, or reform that equilibrium again to being where it exactly was before, where it's to the right but not more in the middle, right? Remember at the start of a reaction, at the start equilibrium was to the right but very slowly, I'm talking about this equilibrium here. Equilibrium to the right but very, very much very little to the right. It's more in the middle, right? When we did that reaction, when we cause it to go to left a bit, once we've maintained the concentrations again, we maintain that balance again, it will return back to its original position. Now, what if we added base to an acidic buffer, right? So it's the same principle right now, but now we're just talking about base, right? So if we added base to the acid buffer solution, the hydrogen ions will react with it and neutralize it, and the unionized methanoic acid will ionize it to produce more H plus ions, and this will reduce the pH change. So if we increase if there's an increase in base, so let's say A minus, so let me just remove this. So let's say we had hydroxide ions, increasing, we added more hydroxide ions to our solution, right? The hydroxide ions will react. Now, it's easy to think that it would react with the NaOH, but if it reacted with NaOH, it wouldn't make much sense, because remember, that forms sodium hydroxide, which is a strong base, which would just dissociate back into Na plus and OH minus again. That's not what it's going to do. It's not going to do this, because that's just going to form sodium hydroxide. What it will do is that the OH minus will react with the H plus, right? Sorry, a little technical issue there. Something just happened, so I had to just end that. But I was saying that the hydroxide ion will react with the H plus to form water. Now that reduces. Now if the hydroxide ion is reacting with the H plus, to form water, you've now reduced the concentration of OH minus, which is what we want to do. We're trying to diminish the concentration of OH minus in solution, because we're trying to get rid of it. Remember, we're trying to maintain a constant pH, and hydroxide ions would increase that pH, right? So if we react the hydroxide ion with the H plus, we're decreasing the concentration of OH minus, but we're also decreasing the concentration of H plus as well. Now the concentration of H plus in solution is already low anyway, but if we decrease it even further, what happens now is that equilibrium or this direction would shift even further to the right to produce more H plus in our solution. That's all that's happening here, right? So what it's doing is that we're shifting equilibrium to the right to produce more H. So H plus concentration is OH minus is reacting with H plus, and that reduces the concentration of OH minus as it forms water, but it's also decreasing the concentration of H plus. But also, as it decreases the concentration of H plus in our solution, that causes equilibrium to shift to the right to produce to increase the concentration of H plus, and that would obviously decrease the concentration of our methanoic acid in our solution, right? Now, it will continue doing this until all the OH minus is removed from our solution, right? There comes a point, like I was saying, like this graph shows here. I said this was acting as a buffer until here, right? Until we reach our equivalence point, where the concentration of OH minus is greater and is equal to or greater than the concentration of H plus in our solution, and that causes we lose the property of our buffer at that point, and it no longer acts as a buffer. But until that point, as you can see here, it consistently maintains that pH. Now, it's not going to be accurately that pH, but consistently maintains that pH roughly, right? And that's what's happening here, right? So we're increasing as hydroxide concentration increases, because as I said, this is a buffer, but we've had to change the condition where it's become more basic. So increase in hydroxide concentration, it will react with the H plus in our solution, and that would decrease the concentration of any OH minus has been added to our solution. As it does that, it also diminishes the concentration of H plus, and that causes the equilibrium to shift to the right to produce more H plus to maintain that constant acidic pH that we're trying to maintain for this buffer. And that's that. And then as it does that, eventually hydroxide concentration will reduce to a point where it's completely used up, and that would be the end of that. We've returned back to our original condition. Now, basic buffers are the same principle but just with bases, right? So a basic buffer has a pH of above 7 and works on a similar principle. A good example is ammonium hydroxide. The equilibrium for this reaction is ammonia plus H2O goes to form ammonium plus hydroxide ion. Adding base shifts equilibrium to the left to remove base, and adding acid shifts equilibrium to the right to remove acid. So as you can see here, a basic buffer is the same principle but just with a base, right? So we have a weak base and a salt of a weak base. Remember, for an acid we used a weak acid and a salt of a weak acid. For a basic buffer, we use a weak base and a salt of a weak base. And it's the same principle, we just use the equilibrium. If we add base, that shifts equilibrium to the left and removes the base, and if we're adding acid, that shifts equilibrium to the right to remove the acid, right? I'll show you what I mean here, right? So I'll write it down here because I get some people can. So we have two equations, right? So one of them is ammonia plus, oh yeah, I'll write down this, plus H2O so ammonia aqueous plus water forms an ammonium ion. I don't like where I write the H. An ammonium ion plus OH minus in our solution. And then the other, so we have a weak base and a salt of a weak base. The weak base, the salt of weak base that we're using is ammonium chloride. Now, so I'm going to show this here. You don't have to write this in your actual thing. I'm just showing that they cancel each other out there. That's ammonium chloride. Now, same principle now, but I guess the equilibriums are slightly, would be reversed, right? Same principle, just reversed because now we're having a base. So NH4 plus aqueous. And when I mean reverse, I mean this, if we change the conditions, it will be in a reverse method, but they still act in the same way. So what I mean, I'll show you what I mean here because I don't want to confuse people too much. So plus Cl minus. So it's still going to be here where we have a situation where it's a weak base, right? It's a weak base. So equilibrium is going to be slightly to the right because it does dissociate hydroxide ions in solution or A minus in solution, but it does it very weakly. And then this is a salt, so it fully dissociates ions in solution, so it'll be far to the right. So here we have a low concentration of ammonium ions and a low concentration of hydroxide ions, and a high concentration of our reactants. But it's the opposite here, where you have, this is a salt, right? So the salt will have a high concentration of our products because it fully dissociates ions in solution, and therefore they have, because it fully dissociates, we have a low concentration of our reactants. Now, it's if we add more base to this, right? So if we increase the base, so say we increase the concentration of hydroxide ions, right? So if we increase the concentration of hydroxide ions in our solution, not what I was looking for, and all of a sudden it's now high, all this does is that now we have a high concentration of our of hydroxides in solution. It just causes equilibrium to shift to the left. It just forces equilibrium, and you think, so but we already have high concentration, a low concentration of NH4. How is it going to make sure we use up all of the NH4? Remember, we have a high concentration of NH4. This is all in the same beaker. Two separate equilibrium reactions, but all in the same beaker. So we do actually have, if all of this NH4 plus gets used up, it will just use NH4 plus from the second reaction here, and that will make sure that we have equilibrium shifting to the left to reduce any increase to the concentration of hydroxide ions in our solution. Eventually, and that would diminish the concentration of OH minus in solution. and bring it back to sorry. Bring it back to its original low concentration to maintain bringing concentration back. It's important that you mention that you're bringing the pH back to its original, the pH that it's trying to maintain in the buffer. So the conditions are just me, and to do that, if we're trying to maintain that pH or bring the pH back to its original pH of that buffer solution, we have to maintain original conditions. The conditions determine the pH. Now, if we increase the concentration of H plus in our solution, right? If we added more base, so if we added more acid, so we increased. Sorry, I'm streaming right now, so bear with me. Yeah, but if we increase the concentration of H plus in solution, it's high. It's just gonna react to the OH minus, right? So that, and then once that happens, we're using up all of our hydroxide ions in our solution to reduce the concentration of H plus, and that will cause equilibrium to shift to the right, because remember I said we're using up all our H plus to form OH minus. As we do that, we're decreasing the acid, by the way, so pH will come back up again, because I'll restart this again, because I think maybe I'm smuddling my words. If we increase the concentration of H plus, pH will decrease, right? So the change to condition is in adding an acid to this basic buffer. So the change to condition is adding acid, and that decreases the pH. Now, to counter this, what the buffer does, it would the acid will react with the hydroxide ions in a solution, right? And it will, as it does so, it will use up the concentration of H plus as it's reacting with the hydroxide ions. But in doing so, also we're decreasing our concentration of OH minus in solution even further than it originally is. And so what happens here is that equilibrium of this top reaction will shift to the right to increase the concentration of hydroxide ions, so that we return back to our original conditions, and we have we return back to the same concentration of hydroxide ions that we have, unless the concentration of H plus is too great, and in doing so, you get what we had here. Is maintained a constant pH, right? And then once the equilibrium point has been breached, I should say, we get to this point here. Now, I've explained what the two buffers are. Now, I will leave. I probably said I left the link in one of my previous videos, but I'd say check out Anaerobic Chemistry's videos that go into more depth about how to answer. His videos are much better than my videos. I can say that for certain, about how to actually answer some of these questions. And talking, I've explained some of what the buffers are and how they react. So if you want to do format questions related to that, that's fine. But it's more exam questions in terms of how to answer some of these questions that are related to this. That's going to be in his video. I'll also do another separate video, but his videos are definitely the best, so I say check him out. I'll leave a link in the description to his videos that are related to that topic. But I'll say calculations of buffer solutions, right? So buffer solutions have a specific pH which can be calculated. Now, the assumption is that all you need to know that to calculate the pH of a buffer solution is its Ka, because you need to make a couple of reasonable assumptions, right? That the salt is fully dissociated, as we've already said, and that the acid is pretty much unionized. It doesn't. It's very weak in dissociating in solution. That's what weak acids are. They weakly dissociate H plus ions in solution, so we can assume that they're almost unionized. Now, we write down our equation for Ka. This is how we go about it, right? We're just rearranging our equation, right? So we know that Ka is equal to H plus times by A minus over HA. If you don't remember that, or watch my previous video that I talked about that. But remember, all acids would follow. This is just an equilibrium, right? Acid dissociation constant. So in a previous video, I explained how that works, right? But remember that if that's representing our acid, right, H plus and A minus, right, unionized acid, then we would dissociate our acid into H plus our A minus. And if a dissociation constant, always products over reactants. And that's what the Ka represents, right? If you want to work out the H plus concentration, so if we want to work out the pH from the Ka, remember, if you want to work out pH, the very first thing we do, right, is write down our equation. But what do we need from this equation? we want to work out the H plus concentration. Because if we want to work out the pH, we need the concentration of H plus. But we don't have that. We have our Ka, we may have our A minus concentration, and we have our HA. So if that's the case, and if you don't, it all depends on the conditions, but say that we had our Ka, HA, and A minus, worked that out somehow, right? And all we need is a H plus. We need to rearrange this equation into H plus is equal to Ka times by HA over A minus. We assume that the salt is fully dissociated, so A minus just the initial salt concentration, and we assume the HA is unionized, so that's just an initial acid concentration. Now, depending on your conditions, you may get a situation here where Ka is equal to H plus squared, because the concentration of H plus and A minus in your solution is equal, because it's a very, very weak acid or weak base, but you may be given this condition where H plus is equal to A minus, and it's if you know that, and there'll be certain questions where it's particularly obvious. I said go to Irie Chemistry videos. His videos are probably one of the best in explaining that. And I'll try and do some example questions in the next video. But once you understand that, and you just know that if these are equal, H plus, then K is equal to H plus squared over HA. Rearrange this equation into, rearrange this equation is equal to H plus is equal to, really, it's just square root of Ka times by HA. And you will get questions where you have to do this. And if you can rearrange equations, this is no big problem for you. And that's in relation to this. So I'll do some example questions later on, but hopefully this video was helpful to you.